Hello, so welcome to my talk. I'm Mikio Braun, and I'm going to talk about real-time event processing with stream mining. And as you can see, beyond scaling. So this is actually, like, I mean, we've heard all these talks about Hadoop, and everyone tells you that you have to put all your data in the cluster first, and you need a big data to handle all that data. But actually, if you look into it, there are algorithmic approaches beyond scaling, which allow you to deal with quite a big amount of data in real time. And I'm going to talk a bit about that, okay? So, yeah, a lot of the data if you look at big data, right, a lot of the data is actually event data, right? The question with big data is always how did it get so big? And one of the possibilities is that you have events and you have lots of events, okay? And there are many different areas. For example, if you have financial data, or if you have like a gaming app and you collect all the events of all the people who play the game, then you can get a lot of data very quickly. And usually what you're interested in is, you have all these events and they are sort of unstructured and you want to know, okay, what's actually happening in there. So, for example, is there anything which occurs very often or very rarely? And what are the people, how many people are playing my game? What is the average time, right? So basically, the first thing you usually want to extract are very basic statistics from your data. Okay, and there are basically two problems with the event data, and one is that you have a lot of data. So if you start with only, let's say, 100 events per second, which is really not much, then you end up with 3.2 billion events per year. And if each of the event has, I don't know, a kilobyte or so, then you already have a lot of data to store and also to process. Okay, another problem with data is that potentially your events are talking about many, many different kinds of events. For example, if you have tweets or something, like in English, and if you just want to count how often a word occurs, then you already have the problem that you have potentially a large number of distinct words, right? Or even if you, I don't know, if you have a website and you look at all the people who come to your website, it might easily be that the IP addresses which originate the accesses, they're in the millions and so on, right? So you have to, so even if you just want to do simple statistics, you already have the problem that you have to count millions of distinct objects and also for many, many different events. Okay. So how do you do this usually? And usually what people tell you is you should just scale, right? So I mean, so here I try to sort of picture the real-time landscape. So at the top, SQL, so this just stands for like the traditional approach. You just put everything in the database. And then if you want to count, you just do some select count, whatever, right? And then you get out the statistics you're interested in. But the problem is that, of course, it's quite slow because it's like one huge disk and probably it's too much information. And doing this aggregation takes a lot of time. And people have developed different kinds of approaches to deal with that. So one problem with this SQL in the traditional sense is that often like each row in the database is stored in memory. So if you're just interested in aggregating over one of the columns, you have to do lots of seeks to actually extract this column, right? Because for each row you go in there and say, okay, just give me that and then give me that, and they're all scattered over the database. And people invented for that, so that's like the first on the left here. So there are things like columnar databases which are actually organized in columns, and then you can just do a seek over a column very quickly because it's just it's continuously on the disk. So that's one thing. And there are many products out there who say, okay, we do real-time event analysis, but actually they are just a columnar database, right? Then the second problem is, of course, you could say, okay, I store everything on disk, which is the main problem why it's so slow, so let's just move to in-memory, right? And then there are also products out there who say, okay, no, we do like MapReduce in memory, and we're also real-time. Then there is the problem always that if you first store the data and you want to analyze it later, you have this, the computation takes some time. So even if you scale out, it takes some time between you issue the query and you get the results. So there are people, their approach is to say, okay, we don't just store the data and then process it later, but we just process it as it comes in. So we have something that's like stream processing. And then there are even people who say, okay, stream processing is still too complex. I want to have a nice DSL where I can just issue something like a stream query, and then I get the aggregates out, and then you end up with something like complex event processing. Okay, so I mean, all these are, I mean, and, of course, you also have combinations. You can have like a columnar database, which is in memory, or you can have let's see, stream processing is always in memory. Yeah. But I mean, so like if you talk about real time, there are actually many different approaches. And even if you say, this is still not enough, I can always scale out, right? And then you end up with something with like a Hadoop or Storm. But there's there's an alternative route which I'm going to talk about now, and that is not to scale, but actually to like say, okay, I just have one computer and I don't want to buy more, but instead to see whether there are algorithms which allow me to deal with that data, still like on a single machine. Okay, and the key to that is that you start to approximate. So you say, if I want to count 100 million counts, I don't want to store 100 million counts. I just want to focus on that, which is important to me. So that's the basic idea. Okay, so stream mining. Stream mining algorithms. So this is a set of algorithms which have been developed in the field of data mining in the mid-2000s. And the basic idea is that you have an infinite stream of data down here. Okay. And you have an analyzer which has bounded resources. So this normally means you only have a fixed amount of memory, but you're still interested in answering certain stream queries. And the most basic ones are, for example, how often does an item appear in the stream? Right, so I have the stream, and I just want to, let's say it's IP addresses, and I want to know how often did a certain IP address occur in the stream. Another question is how many distinct elements are in the stream. So I'm not interested in like counting, but I just want to know how many different ones are in there. So it's more like a 0-1 counting kind of thing. And then probably the most complex of these basic things is what are the top K most frequent items. So I not only want to count like individual items, but I also want to get like a ranking of them, right? And all with these bounded resources. Okay, so how do such algorithms look? Okay. And so obviously, right, if you want to count items, but you only have bounded resources, you have to throw away some piece of information because otherwise it can't work, right? And usually, so one way to picture this is this triangle here. So on the top we have big data, so you want to be able to process lots of data. You want on the lower left side you have that you want to be fast, right? So in the sense of you can handle a lot of data and also get results in a short amount of time. And then on the other hand, we have exact. And sort of MapReduce and friends, they say, okay, we are big data and exact, but you can't be fast. Right? So this is like this cap theorem, which says you can only have like two sides of the triangle. And stream mining, on the other hand, says, okay, I want to be able to process a large amount of data, and I want to be very quick, but I don't care so much about the exactness of the results. Okay. So actually, I start with the last problem, so this top case. So how do these algorithms look like? And the interesting thing is about these algorithms is that they are often quite simple. So for example, with these heavy hitters, the idea is as follows. So you want to count how often an item occurs. And you have a fixed table of counts, right? So you only have a fixed amount of memory. And these are just the keys you are counting, and these are the counters here. And now if a new element occurs in your stream, you have to have two choices. So either it's already in the table, and then you just update the count, or if it's not in the table, then you just remove the entry which has the lowest count, but you also use this count as a starting point for the new item, right? So here, and then okay. And that way, so this is something like a worst case lower bound on the numbers of times I might have seen that item but missed it because it has already been in the table, but then it got deleted from the table, and now it occurs again. But this is sort of like the lower bound, and based on that, you get some performance guarantees. Okay? And of course, the larger the table is, the more exact your results are, which also depends on the distribution of the data. So it's a quite simple algorithm, but you can very quickly get the top K elements from that. So another thing. A problem often is that you are not really interested in having these top K or these heavy hitters for the stream, for all of the stream, but only for a given time window, right? So it's not like you start the algorithm and then after 2 years you still have like the top items for the last 2 years, but only you're interested in the last week or last month or so. And if you want to do that exactly, that's also something which can be quite difficult because you really have to at least remember all the events for the time frame you're considering. Because even like if you count up when they come into the time window, and then you count down when they leave the time window, you still have to keep this data somewhere. And if you're aggregating over a month or so, this takes a lot of time. An alternative is to use exponential decay. Okay, so instead of just like going one up and one down when the event occurs, actually the count of the event decays over time. So after, let's say, after an hour, so when it occurs, you have a count of 1, and after an hour, it goes down to 1/2, and then to a quarter, and like that. Okay. So it's not exactly like over this time window, but you still get an aggregate which has a certain time scale with it. Okay, and the nice thing about this is that it's actually, you can implement it in a very efficient way. So, okay, when you write this exponential decay down, basically, you get this formula here. So this is the decay part where you have the time differences, and this is the score which you put in there. And the nice thing about the sum is that it's actually recursive. So in order to get the score for the next element, you have like the count, and then you have something which is like a time shift term, which you put on the score you had before. So you don't have to aggregate, keep all the data and aggregate all the time, but you only have to remember the timestamp of the last event and the last score you have. So only 2 numbers. Okay. So if you write that down in pseudocode, basically you have 2 tables, the counters and the timestamps, and then you have 2 operations. One is the update when an event occurs, and the other is, in order to get the score, you get something like this, right? And you always just have the count, and you have this weighting term, which is like a reweighting over time. Okay. So I'll come back later as an example for that. Another sort of a class of algorithms are so-called sketch algorithms, which sort of try to approximate a histogram over certain elements with a fixed amount of memory. And so they work in a way a bit like these Bloom filters. I don't know if you know them. But the idea is that you have, like in this direction, you have m bins, and you use n different hash functions for each of these rows, right? And if you get an item, you compute all these different hash functions, which gives you a different index for each of the rows, which sort of is like a fingerprint for that item. And then you count up all the cells which these hash functions have indicated. And of course, you will get collisions, but the idea is now, if you do the query, you take the minimum over all these entries, and this sort of minimizes the amount of collisions you have, and therefore you get a good estimate of your data. Okay? So this is something which is very efficient if you want to approximate counts over very large spaces with very few memory, but compared to this thing with the heavy hitters, you don't get this ordering here, right? Because you don't really know what's in there. It's just like this bit field, and you don't store the keys which are in there. But if you want to query, you can just query anything and get an approximate answer here. Okay, so these are two algorithms which are fairly simple, but also somehow very boring, right? Because they just do counting over certain time frames. I mean, in a way, getting the top most active items is already useful if you're in like some analytics kind of application and you just want to know what the most active things are. This is already nice. But what else can we do with it? And it turns out, so this is in the second part of the talk, I'm going to give you a few examples on that. You can actually do quite a lot of stuff with simple counting, because if you think about it, counting is statistics. Okay? So I've written down here like 3 basic statistical quantities, like a mean, so you just want to estimate the average, or a correlation, or even like a principal component analysis. So this is something where if you have vectorial data, you want to know what the main directions are in that space. And if you look at it, right, so it's always, in the end, you always aggregate some sums. Okay? And you could do this not only just with overall time, but you could also insert a time scale in there, and also this weighting, so that you get these statistics based on data which belongs to a certain time frame. So you could, for example, say, what is the average of that quantity over the last hour, or average over the last minute, over the last day, or something. Okay, and that you can already get based on these algorithms, without doing a lot of computation, because you just update each event as it comes in, and for each item type, you only need to store 2 numbers. Okay. Yeah. So just slightly more complex example is the least squares regression. So this is a simple method for doing predictions on real-valued functions. So basically what you have to do is you have to compute these beta hat, right? So this is just in matrix notation. It's a very simple. You just have to write down this X transpose X matrix and invert it. And if you don't have too many features, then this is probably okay because it's just a D times D matrix. So if D is a few hundred or so, you're okay. And these are the entries of this matrix, right? But this is again a sum, which could be used. But you could also just, as I said, use this exponential decay to aggregate these sums over a certain time frame, right? Do these 2 updates for each element you get. And then you can sort of online learn these predictions based on a certain amount of data, right? So you could have, you track something which changes a bit over time, and you could have a prediction which is always based on the last hour or last day of your data without actually having to go back and crunch all the data because you just track these numbers. Okay? So you could also just learn probabilistic models based on the data, just again because these are just numbers, okay? And if you have that, so for example, if you compute the mean and the variance, you could already do something like outlier detection, right? So the idea is that you compute some statistics. So this is the data you've already seen so far, and this is like your future data. And this line here is the weighting factor, which says how much this data contributes to your estimate. And then you have a probabilistic model. If you get a new point, then you can ask, so given the data I've seen and the model I've inferred from my data, how probable is it that I see this point? And if this probability goes below a threshold, you can do outlier detection. So you say, okay, this looks very improbable, probably something's not happening here. And this is something you could use very well for monitoring or other kinds of approaches. Okay, but I mean, you can even do more. So there's a paper which describes how you can use these countment sketches to aggregate all the information you need in order to do online clustering. So in clustering, the idea is basically you get new points and you have like centroids, I mean like centers for each of the classes, and then you just assign the new point to the closest class, right? And then you update the class. So you get the points are sort of like you start with random points, and if you just assign new points to the closest center you have, and over time you just get the clusters which describe your data well. And this is a problem if you're clustering text documents, your spaces can become very large because you have these potentially 1,500 words. But using these countment sketches, you can actually keep these statistics in a very compact manner in memory. Okay. Right, so and if you start to think about it that way, okay, it's only counts, and if you dig in and look at especially statistical methods, like classical statistical methods, which have been around for quite some time, they're all based on simple statistical estimators like numbers. So for example, TF-IDF, which is a measure which you use to weight words based on how often they occur, right? So a word like the, because the occurs in all documents with very high probability, it's really not that surprising if the occurs very often in a document. And that's something you can also track in real time based on these algorithms, because it just counts, right? So for each word you would do like an update for the word, and you would do another update to count the number of documents you have, and then you get this IDF score based on just from the statistics you've collected. And the interesting thing about this is that this is something which automatically tracks the data you actually have, right? So if people suddenly start talking about a certain topic, after some time, you've just adapted to these statistics, and you actually start to downweight these words. So they are not that surprising anymore because, like in the last hour, they have been very, very frequent in your data. Right? And again, this is something which you can just track. I mean, even for words, you just need a few megabytes, 100 megabytes, something. It's not something where you will have to store the data first, and then you have to crunch like a day of tweets or whatever to get this kind of thing. You can just do it in online fashion. So just to give you an idea how complex these things can get, you can even do classification based on naive Bayes. So naive Bayes is like a baseline method. So if you ask a machine learning guy, they say, naive Bayes, isn't that like the simple thing you can do? So it's always used as a baseline to compare your own method against. But actually, it's not so bad as people say, right? So basically, this is the formula you use to do the prediction, right? You see again, it's a sum. And most importantly, the numbers which are in there, they are all also very simple kind of statistics, like how often a word occurred in the document, number of times the word appeared in a certain class, so things like that. And then there is also this nice paper tackling the poor assumption of naive Bayes text classifiers, where they present so 7 heuristics with which to make naive Bayes perform almost as good as a support vector machine for text classification. And these are all, again, things which you can just compute in just the same way doing these updates, right? So you can just stream in your data. For example, you could use this to predict hashtags on Twitter, right? So you just see the hashtags which you have, and you can then use these as training examples in an online fashion, so that you can also predict hashtags for tweets which don't have hashtags or which don't have these special hashtags. And this is again something which automatically tracks based on the whatever time scale you're interested in. Right? So this is not something where you store your data first, and then once a week you crunch it and you learn for a long time, and then you have a new predictor. But this is something which just updates, which is just updated all the time. Okay. So these were all very simple methods based on statistics. But if you take something more advanced, like a support vector machine, the question is, could this technique also work there? And it's actually not so simple. So the function you learn in a support vector machine is something like that, and actually that's the sum over all the points you have. And this is not something which you can. So it's not like in the example with the linear regression where you only have a fixed set of statistics. Of things to track, but here actually you have a big matrix which contains all the data, and for training you need to do a lot of computation with that data, so you cannot really do it. But you could still use stream mining, for example, to cluster and then to extract an representative test for your data set. Okay, so if you want to play around with that, so actually we have built something called StreamDrill, which is exactly that. So it gives you this basic layer, not the statistic methods I talked about, but the basic layer to do this counting. So if you want to play around with this kind of technology, this is something you can just download there, you start it, and then there's a REST interface where you can talk with the thing. And basically what you pipe in are tuples, so you have to predefine beforehand what the structure is, but then the events are just tuples where you say, okay, this word and this word occur together or something. And then you get these top K trends for different time scales which you can just query. And for example, we did a simple demo based on these stock symbols. So I don't know if you've seen this before, but actually there are people who are using the stock ticker symbols on Twitter to talk about certain companies. And what we did is we extracted those and then, for example, looked at combinations at co-occurrences between these symbols and certain keywords, right? So here you would, for the symbol apple and the keyword apple, okay, that's not so surprising, you would get this number of occurrences over the last day. And then you can build something like this here. So in this graph, what we've plotted are the symbols and the keywords and the connections between them. Okay, and this is again something, and then you would see over time how this bobbles and things go get smaller and larger, and it's really something which can work in real time. Oh. Okay, so the summary. So although everyone says, okay, you first need a big Hadoop cluster, and you have to scale if you want to do big data, there are actually alternatives where you can just take some data, pipe in, I don't know, a few 50,000 events per second, and actually see something which is in your data without, doing this initial investment. And stream mining is a class of algorithms which work pretty well for that. And the idea is always that you say, okay, it doesn't have to be exact, so it's okay if it's approximative. But for many applications, it actually is, right? Especially if you're just interested in the most active ones, but you're not really interested in the exact numbers, it's okay to get approximate results. And you still can sort of do this, use this kind of approach to get something in real time, and then if you're really interested in the exact numbers, you can still crunch it later, right? But you don't have to do this and try to scale your Hadoop cluster to a size where you can actually handle event streams in real time, because it's something which is very expensive. So it's better if you have a cluster which you can like run once a day and use something like this in front of it to get your real-time results out there. Okay, and if you want to play with it, you can look at StreamDrill, which is something we've built to help you get started with that. Okay, thank you very much.